I want to reconsider the dimensional analysis, that is the chain rule. And here's this function, tangent cubed of the square root of 3x squared minus 1. Now, if we go to the inside out of this function, let's just think from the inside out, because if this is a composition of a bunch of functions, the first function is 3x squared minus 1. Right? That's when you give this function an x, first it squares it, multiplies by 3, and then subtracts 1. Then it takes the square root of that. Then it takes the tangent of whatever that is, and then cubes whatever that is. Right? So you should be able to see that. Rewind, pause, and play it again if you can't get it. Okay, so let's just think about this a little bit backwards from the outside inside way, and let's think about the inside outside. The last derivative we're going to take is the derivative of the inside. It's going to be the derivative of what's under in blue. And what derivative is that going to be? That's going to be the derivative with respect to x of 3x squared minus 1. Now I'm going to write a whole bunch of terms here, and the reason is going to be perfectly clear, hopefully, in just a minute. So this is the last thing we're going to take. Let's take this term d of 3x squared with respect to 1, and I'm going to put that here, d of 3x squared minus 1. And now, what's the next thing that the function does to its argument? Well, like I said, the first thing it does is 3x squared minus 1. We took care of that. And the next thing it does is it takes the square root of 3x squared minus 1, or it raises it to a half power. So what I'm going to do is I'm going to change color. So it raises it to the 1/2 power. So I'm going to write d of 3x squared minus 1 raised to the 1/2 power. Hopefully someone's going to get that. Now, we're going to take this and we're going to take this and write it in the denominator of this next multiplicand, I guess is the right way to call it, d of 3x squared minus 1 to the 1/2 power. Well, after we take the square root of this thing, what's the next thing we do? We take the tangent of it, right? It says, you say, well, no, we took the tangent cubed of it, but we take the tangent of it and then we cube it. So let's just remember that this is the tangent, right? We first take the tangent and then cube that. So I'm going to write d of tangent of 3x squared minus 1 to the 1/2 power. Okay, if you stay with me till the end, I promise there's huge dividends you'll get paid in huge dividends. Okay, so and this whole thing is in the tangent, right? It's a tangent of this. So I think, and we're taking the derivative. Okay, and then what's the next thing that this function does? I just said it. It cubes the tangent, right? So I'm going to write derivative. I'm sorry. Let's not skip any steps. I'm going to take this term right here. I'm going to put that in the bottom. I'm going to put that in the basement. D of tangent of 3x squared minus 1 to the 1/2 power, right? So I'm going to get my eraser off of the blackboard. And now we write the whole function, d of tangent, don't worry, I'm going to get to the cubed part, of the square root of 3x squared minus 1. I lost the 1/2 power there. I'll put the 1/2 power there instead of the square root. Okay, 3x squared minus 1 raised to the 1/2, and that whole thing cubed. Okay, so why is this really the derivative? Well, by design, I put each one of these terms, and you cannot do this. You cannot just cancel and move on your way. But this is the theory, at least. These terms are the same, so I can cancel them. These two terms are the same, so I can cancel them. These two terms are the same, so I can cancel them. We're left with the derivative with respect to x of tangent of 3x squared minus 1 to the 1/2 raised to the 3rd power. Well, that's what I was asking for up here. So that's why it works. Now let's take some derivatives. So do you want to work left to right or right to left? I'm going to work from left to right. It's very satisfying. The derivative of this thing raised to the 3rd power with respect to this thing is just 3 times the thing, x squared minus 1 raised to the 1/2 power, and then squared. Okay, I'm just going to put the squared there because that's sort of the convention. Times the derivative of the tangent of this thing with respect to that. Oh, I'm sorry, the derivative of the tangent with respect, the derivative of tangent of this thing with respect to this thing. Well, the derivative of tangent is secant squared of whatever the thing is. 3x squared minus 1 to the 1/2 power. I guess I should put this in brackets too. What's the derivative of something raised to the 1/2 power with respect to that something? This is just equal to 1/2 3x squared minus 1, the something, raised to the negative 1/2. What's the derivative of 3x squared minus 1 with respect to x? Oh, Mr. Steiner, that's easy. That's just 6x. So this is your answer, and we could combine like terms here or to cancel stuff, bring some stuff to the denominator. But if we're careful, right? So we have 6 cancels with 2, leaves 3, and the answer, and we have 3x times 3, so let's say 9x tangent squared of the square root of 3x squared minus 1 times secant squared of 3x minus 1, square root of that thing, 3x squared minus 1, all over the square root of 3x squared minus 1. Okay, look at my notes on the video link that I sent you, because that will help explain why this is the best thing since sliced bread, and in other ways it's the worst thing ever. Okay. Oh, you know what? I shouldn't leave it like that because you're not going to read the notes. Okay, so why is it really good? Well, you can see I just did it in the whole thing in like 3 steps, right? I didn't have to. Everything worked right down. But it is a ton of writing. If you do this for every single time you have to do the chain rule, you're going to get clobbered with time constraints. So this is the right way to think about the chain rule instead of just the mechanics. This is the absolute correct way to think about the chain rule. However, if you rely on this as a crutch for really, really simple problems where the chain rule just has to be applied once, you'll spend too much time. It's almost like you learn the multiplication tables, and yes, you could go and draw an array of 4 by 5 things and count to 20 every single time, but you'd spend way too much time doing that, right? You just have to know. If you just see it, you should be able to apply the chain rule. So the trick for you might be to recognize when this dimensional analysis, when working from the inside out with many, many steps of the chain rule, might be really the best way to go. Okay, so there, I said it.